Greetings, my name is Guryanov Aleksey, and I will present my work efficient computation of SHAP values for piecewise linear decision trees. The overview of my presentation is as follows. At first, I will talk about the interpretability of machine learning models. Then I'll discuss the machine learning models of decision trees and piecewise linear decision trees. Then I'll describe the main contribution of my work, an algorithm for efficient interpretation of piecewise linear decision trees, and in the end I will give a quick rundown of experimental results. Machine learning models are used in more and more areas and industries and affect more and more of our life. Robust usage of machine learning models requires an understanding of why the model makes certain predictions and/or decisions. Currently, many different approaches exist for interpretation of different classes of machine learning models. One of these approaches is called SHAP values. SHAP values is a unified way for interpretation of machine learning models. This approach decomposes prediction of machine learning model into components attributed to each feature in a way that satisfies several important properties. SHAP values of an arbitrary machine learning model can be computed by evaluating the model an exponential number of times with regards to number of features. This algorithm can be useful but only in scenarios with a model of small complexity, scenarios with a limited number of features, or scenarios with a big amount of computational resources, which limit the applicability of such approach. Decision tree is a basic type of machine learning model. This type of model and ensembles based on it constitute the foundation of one of the most popular machine learning libraries, such as XGBoost, LightGBM, and CutBoost. It was shown that it is possible to efficiently compute SHAP values of decision trees and additive ensembles of such trees. Piecewise linear decision trees use linear functions over feature space as output in leaves instead of constant values. Such trees and ensembles based on such trees can achieve superior quality compared to models based on regular decision trees. Algorithms for training of several subtypes of such models were explored in recent works. 3 subtypes of piecewise linear decision trees are studied in my work. A piecewise linear decision tree type 1 is a binary decision tree where predictions in the leaves are linear functions over all features. A piecewise linear decision tree type 2 is a piecewise linear decision tree type 1 with an additional condition that linear functions in the leaves can only use features that participated in the decision rules of all nodes that lead to this leaf. A piecewise linear decision tree type 3 is a piecewise linear decision tree type 2 in which the linear coefficients for a specific feature in the leaf are tied to the node that leads to this leaf, which uses a decision rule over this feature, and linear coefficients for a feature are equal in all leaves of left and right subtree of this node. Main contribution of this work is development of an algorithm for efficient computation of SHAP values of piecewise linear decision trees of different types and proof of algorithmic complexities of such suggested algorithms. The algorithmic overview is as follows. First, we decompose piecewise linear decision tree into a sum of limited number of basic predictors. Then we suggest an algorithm for efficient computation of SHAP values of basic predictors. And then we use SHAP property of additivity and compute SHAP values of original piecewise linear decision tree. In the next slides, we'll use a certain notation. By L will denote number of leaves in the decision tree, by D will denote the depth of a decision tree, and by M will denote number of features the models are trained on. The base predictors we are studying are as follows. Constant leaf predictor is a decision tree which has precisely one non-zero leaf value. Linear leaf predictor is a piecewise linear decision tree type 1 which has precisely one non-zero linear coefficient in all leaves, and the leaf with a non-zero linear coefficient has an expected output value of 0. It can be shown that it is possible to represent a decision tree as a sum of no more than L constant leaf predictors, with a depth no more than D. It is also possible to represent the piecewise linear decision tree type 1 as a sum of no more than L constant leaf predictors at no more than N multiplied by L linear leaf predictors, type 2 as a sum of no more than L constant leaf predictors and no more than D multiplied by L linear leaf predictors, type 3 as a sum of no more than L constant leaf predictors and no more than 2 multiplied by L minus 2 linear leaf predictors, all with depth no more than D. It is possible to compute SHAP values of constant leaf predictor and linear leaf predictor with depth D with an algorithm with complexity big O from D squared. Based on the remarks before, it is possible to compute SHAP values of regular decision trees with an algorithm with algorithmic complexity big O from LD squared, piecewise linear decision tree type 1 with an algorithm with algorithmic complexity big O from MLD squared, for piecewise linear decision tree type 2 an algorithm big O from LD cubed, and for piecewise linear decision tree type 3 with an algorithm with algorithmic complexity big O from LD squared. Suggested algorithm was implemented using programming language Python. Experimental evaluation was conducted on a publicly available dataset Higgs, which consists of 11 million objects with 28 real-valued features. An ensemble of 100 piecewise linear decision trees type 3 was trained with different number of first features chosen and different maximum tree depth. Suggested algorithm shows an improvement in computation time compared to brute force algorithm. Thank you for the attention.